Hello everybody, this is a video about the second part of chapter 1 about using and making calculation in the Z over NZ set. So, what is a set? What are its elements? What kind of calculation can we make in this set? All those questions are the purpose of the following videos. Actually, the Z over NZ set has a property that it's a finite set. So actually, perhaps you do calculation mainly in math and physics with infinite sets, or just such as a set of rational numbers, real number, complex numbers. Here we will talk about a totally different kind of set. It's a finite set, and actually, this set contains only n different elements. So apart from that, the question is, how is this set built? How can we make calculation? What is the nature of its elements? So actually, as you can guess, the Z over NZ set is built around the value of n. So it's built from n, and actually from the Euclidean division by n. So that's how n is kind of parameter for all this set. Actually, we will take examples with several different values of n to show you how all this works. Okay, so remind that by the Euclidean division, if you divide any number by n, you will get a quotient, and you will also get a remainder. And actually, to build the Z over NZ set, we will sort of forget about the value of the quotient and focus only on the remainder. So, you know that, actually it's the topic of the very first video of this course, by dividing by n, the remainder goes from 0 to n minus 1. These are all the possible values for the remainder when one makes an Euclidean division of any number by n. And of course, if you count from 0 to n minus 1, you have n possible different values. That has a strong link to the fact that Z over NZ has n elements. So let's take an example to show how this remainder can sort of create or build the Z over NZ set. So example, let's take a little value for n. N is equal to 7. That will help us have simple example. And let's consider 3 different numbers. A is 12, B is 5, C is 19. And now let's make the Euclidean division of A, then B, then C by n. So 12 divided by 7, the quotient is 1, the remainder is 5, and I've stated before, let's forget about that. For B, same thing, 5 divided by 7, the quotient is 0, the remainder is 5. This we don't care about. At last, 19 divided by 7, the quotient is 2, the remainder is 5. So if we just have a look to those three Euclidean division, we find that both A, B, and C have exactly the same remainder, which is 5, when they are divided by n, which is equal to 7. Actually, A, B, and C share we can call a common point or a common thing. All of them have the same remainder when they are divided by 7. And actually, this common point is having the same remainder. This is true for 7. If you choose another value for n, for example, if you choose n is equal to 9, then 12, 5, and 19 won't have the same remainder. It really depends on n. And having the same remainder, so if we go back to some mathematical knowledge from your L1 study, having the same remainder here for n equal to 7, it's an equivalence relationship. And from this kind of relationship, one can build equivalent classes so that we can gather all the numbers which share this common point. Actually, and still to go on with this example, in Z over 7Z, actually, we have an element which is named 5 bar. It's not a number, actually, it's the class of numbers with remainder equal to 5. And this class, of course, contains A, B, and C, that is 12, 5, and 19, but actually an infinity of number. It's equal to 5, 12, 19, we can add 26, and we can find actually an infinity of numbers. Actually, it's 5 plus 7 times k, where k is itself an integer number. That's how an equivalence class or an element in Z over 7Z here is defined. Okay, so for the next video, I will switch back to another value of n and show you how calculation can be made, still using the fact that the elements of Z over NZ are not numbers, they are sets. Nevertheless, we can do some calculation with them and they will be quite useful for further cryptographic purpose.